It's funny. Sometimes the best way to understand right now is to take a good look at the past. And today, we're going to do just that. We're essentially unboxing a time capsule, not of old movies or music, but of pure engineering knowledge. We're diving into a vintage electronics course from 1983 to see the foundational ideas that honestly power every single piece of tech we use today. And this is it, a course from Heathkit/Zenith on transistor circuit design. Now, if you were a hobbyist back in the day, say the 70s or 80s, Heathkit was a legendary name. I mean, these guys were the pioneers of the build-it-yourself electronics movement. You didn't just go out and buy a radio, you built one, and you learned how it worked every step of the way. And you can just feel the spirit of that era in the introduction from the course author Vincent F. Leonard Jr. He signs off with this line, and I just love it. As always, learning is, and should be, fun. And that is exactly the energy we're going for today. All right, so here's our game plan. First, we'll peek inside what one of these 1983 kits actually looked like. Then, we're going to demystify the transistor itself. After that, we'll see how you use one to build a basic amplifier. Then we'll get into the really tricky part, the art of making a circuit stable. And finally, we'll bring it all back to the workbench. So let's do this. Picture it. It's 1983. There are no drag-and-drop circuit simulators, no YouTube tutorials. If you wanted to understand electronics, you had to get your hands on actual components and build something real. You had to get your hands dirty. And that was the whole idea behind Heathkit. It was all about empowerment. The core belief was that the absolute best way to understand how something works was to build it yourself, piece by piece, right from the ground up. So what was actually in the kit? Well, you'd get this whole packet of parts, classic transistors like the 2N394, a few diodes, an LED, even a 741 op-amp. These weren't just symbols in a textbook. They were real, physical things you could hold and experiment with. Okay, now we get to the absolute star of the show, the transistor. It's not an exaggeration to say this tiny little device is the fundamental building block of our entire digital world. And it all starts with this magic material called a semiconductor. The most famous one is silicon, right? It's in this weird middle ground. It's not a great conductor like copper, but it's not an insulator like rubber either. The magic trick is that we can control exactly how well it conducts electricity. And we do that with a process called doping, which basically creates two different flavors of silicon. You get N-type material, which has a bunch of extra electrons, giving it a negative charge. And then you get P-type material, which has a shortage of electrons, creating these things called holes that act like positive charges. You sandwich these materials together in just the right way, and boom, you've got yourself a transistor. So what does a transistor actually do? Well, the simplest analogy is still the best one. Just think of it like an electronic valve or a faucet. A tiny, tiny electrical signal on the input can control a much, much bigger flow of electricity through it. It's like using one finger to turn a handle that controls a fire hose. So let's take that valve idea and see how it works in the real world. One of the most common jobs for a transistor is to make a small signal a lot bigger, inside a circuit we call an amplifier. Okay, so check this out. This is a classic common-emitter amplifier, straight out of the course textbook. You can see the transistor symbol right there in the middle, and it's surrounded by these resistors that are absolutely key to getting it set up properly. So how does this whole thing work? Well, think of it like a theater. The resistors create a nice, stable DC voltage. That's like setting the stage and turning on the house lights. Then, the small AC signal you want to amplify, say music from your phone, that's the performance. It rides right on top of that stable DC level. And this is where it gets really clever. The course teaches this awesome little trick for getting a ton of amplification, or what engineers call gain. You add this one little component, a bypass capacitor. For the stable DC voltage, it does absolutely nothing. But for that AC signal, the performance, it acts like a super fast shortcut to ground, which has the effect of supercharging the whole amplification process. It's such a simple but brilliant bit of design. But here's the thing. Building an amplifier that works is one thing. Building one that works reliably, well, that's the real art of electronics. Early designers ran into this huge problem with stability. I mean, the circuit you design on paper has to work the same way when you build it, right? And it has to work the same tomorrow and the day after that, no matter what. So What could possibly throw it off?
Well, the course points to three main culprits. First, temperature. Transistors just act differently when they get hot or cold. Second, you have leakage currents, tiny, unwanted little trickles of electricity going where they shouldn't. And third, and this was the biggest headache of all, wild variations in the transistor's own gain, a factor called beta. It was just all over the place. You could get two transistors from the exact same box, and one might have a beta that was 400% higher than the other. It's a nightmare for a designer.
So how did they solve this? With a really, really smart circuit design called a voltage divider bias. Basically, instead of depending on the transistor's finicky personality, this design uses a couple of resistors to lock its operating point in place. It makes the circuit almost totally immune to all those problems. Now, you look at this diagram on paper, and yeah, it seems a little more complicated to figure out, right? All those resistors, how do you even start to calculate the voltages? This is where engineers love to pull out some elegant shortcuts. And the course shows you one of the most powerful tools in an engineer's toolkit, Thevenin's theorem. It sounds fancy, but it's this simple three-step process. You can take that whole complicated resistor network and mathematically replace it with one single voltage source and one single resistor. It turns a messy problem into a really simple one. It's like magic. All right, for our last section, let's connect all this amazing theory back to what made Heathkit so special in the first place, the hands-on approach. Because this is what it was all about. This is the magic right here. Taking a schematic, which is really just a blueprint of abstract symbols, and turning it into a working circuit with a handful of real-world parts that you soldered together yourself. That's where the real learning happens. And the course is just filled with these charming little details that remind you how old it is. My absolute favorite is a safety warning. It basically says that if you use modern test equipment that has a three-prong safety ground plug, you could actually blow a fuse in their little training module. It's just a perfect snapshot of a totally different era in electronics. And that brings us to one last thought. You know, we live in this age of incredibly powerful simulators, and all of our gadgets are these sealed black boxes that we're not even supposed to open. So what can we learn from this 1983 course and its get your hands dirty ethos? This core belief that to really understand something, you have to build it, and that learning not only should be, but actually is fun?